just talk through, as I often would when I pass out a test. I just want to make sure that some issues are clear as to what is being asked about, or what a particular number means, what a particular direction or sketch is supposed to look like. And I'm especially feeling that way when we're not here in person, for somebody during the middle of the test to just walk up to the front of the room and ask me, so what did you mean by this number right here, Professor Feig? So I'll do that kind of at the start of our class period time at 11:25, maybe talk about the test for 10 minutes, and then I'll let you kind of do whatever you want. The test will be submitted via Moodle of your work, just your sheets of work, similar to what people have done with homework. Submit that via Moodle by 6 p.m. Monday night, and I will stay on Moodle maybe after 10 or so minutes of just introducing the problems. I'll stay on Moodle if people want to ask questions. And then I think I will pop back onto Moodle sometime Monday afternoon if you're working on the test in the afternoon and have questions. So I think I'll aim to do that at maybe, well, we'll see. I'm thinking 3:30, and my schedule might change. So I'm thinking maybe 10 or so minutes of group time Monday morning to introduce the test, and then you can just kind of work on it that afternoon. I do really ask that it would be your own work. I'm going to kind of indicate what the allowed materials are. What I'm thinking of as allowed materials, I guess since it's on my mind, I might as well say it now. I'm thinking of allowed materials being, too high, this sheet here, which is, I think, called, can't remember what it's called on the Moodle page. It's a one-page summary of most of the key ideas from chapters 10 and 11. Not 100% of the key ideas or equations, but quite close, honestly. And then one other sheet of notes. That's what I'm kind of imagining you can use while working on the test. That's the environment that I would have set up if we were on campus. So I think I'll try to stick close to that. And I'd like you to stick close to that as well. So obviously you have a pretty wide window of time most of Monday afternoon to work on the test if you so choose. One last thing I think I'll mention is the day before the test on the sheets on Moodle. I just don't remember what it's called. It's called Energy Momentum Summary, maybe something like that. I'll bring it up here in a second. I'll bring up Moodle in a second. I think it's last week on Moodle, sometime in the previous week. One last thing I'm going to mention between now and the test is, I think Sunday late afternoon or evening, I'm going to have like an office hour on Moodle for people to stop in and ask questions as they get ready for the test on Monday. So we'll go through some practice problems here today in the next little bit less than an hour. And I'm going to give you quite a few more. There's a folder on Moodle, and between a couple files in that folder, I think there's something like 8 or so practice questions. And more than that if you look at some of the other problems we've done over the last week or so. Some of those we've already done together. And we're going to go through a couple of them, maybe talk about a couple homework questions here today, and then you can kind of look at the other ones. I'm imagining 4 worked out calculation questions preceded by maybe a couple short answer questions for the test. So let me give you a couple. I just forgot my other question. Oh, I just remembered. Yes. Okay. I'm going to give you 2 kind of warm up, kind of short answer. These are calculations, but they're not very in-depth calculation questions that you can think about just to get us going and thinking about a couple things that are irrelevant for the test. So here we go. Let me do one thing. And I'm going to give you a vector. It's going to be in unit vector notation. I'm also going to draw it kind of on a XY coordinate plane. And the question is going to be this. The question is, yeah, it was probably better that way. The question is this. Can you come up with a vector which has a dot product of 0 with the vector I'm going to write down? Maybe I'll stand up. So kind of question one, I'll just say A equals, am I on the screen? Okay, A equals 4 I hat minus 3 j hat. And I'll draw the vector, but the question is, can you find a vector B, such that A dot B equals 0? I think that'll be a good problem to think about. Dot product, of course, this would often represent A could be a force and B could be a displacement, and we're trying to find a vector combination that has 0 dot product. That's a dot. Okay. That's the first one. Think about that a little bit. I said I was going to draw it, but I think I'm actually going to write the other question up. I think I'll describe this one in words. Object A, or I'll just object B, and you're trying to find object C is going to be the question here. Okay, objects A, B, and C are all the same mass. A, B, and C are all the same mass for number 2. I'm kind of writing this in the chat. And I'm going to give you speeds. I'm going to say object A is going 1 meter per second. I'm just going to try to give myself a little more space here. I always do that. Okay. The velocity of A is 1 meter per second. The velocity of B is 7 meters per second. And the question is, how fast should C be going so that its kinetic energy is halfway between A and B? So I'm writing this in the chat. Velocity of A, I didn't spell that right, but close. Velocity of A equals 1 meter per second. Velocity of B is 7 meters per second. What should be the velocity of C so that it has a kinetic energy halfway between A and B? Okay, so let me read what I wrote and see if it's what I wanted it to say. A, B, and C are all the same mass. Velocity of A is 1 meter per second. I meant to say velocity of B is 7 meters per second. Close, I hit the number 2 for some reason. What should be the velocity of C so that it has a kinetic energy halfway between the KE of A and the KE of B? I want you to think about these two problems for a little bit. I'll rewrite the A dot B equals 0. And then we'll talk about these two. I think that'll take about 10 minutes, maybe from now till having talked about these two. And then we'll move on and look at some more involved conservation of energy kind of questions. So it's like VC equals question mark. That's for us to figure out. Question mark, question mark, question mark. All right. Giving you a little bit of time to think about that one. What happens? Okay. I'm going to give you about another minute, and we'll try one of these two. Oops. All right. Are we supposed to put our answers in the chat? I think I'll ask you to in a second. Yeah, but just hold off a bit. Okay. If you had to do only one of these two questions, which one do you think you'd go for? That's a question I ask very often when I throw out multiple thoughts at the same time. Number one, somebody likes the dot products. It might have to do with like how comfortable you are with vector notation, the I-hats and the J-hats. If you like that stuff, you could probably like number one. Let's start with number one. Now, there's more than one answer to number one. There isn't just one vector B that has a dot product of 0. And I should say one more thing. I meant to say, can you find a non-zero vector, capital B, such that A dot B equals 0? Otherwise, it's kind of easy to just kind of come up with the trivial solution. Well, if B is 0, A times B is probably 0. I meant to say, can you come up with a non-zero? Otherwise, it's kind of a boring question. Otherwise, there's a boring answer. Okay. Can somebody tell me how, maybe Darren, I see your name down there. Can somebody tell me like how you would think through number one? I'm going to erase number two and give myself some space here. What's a vector that would work for B? If A dot B is 0, they are perpendicular. So that's the core geometric idea of dot product is, if this is 0, either A is the 0 vector, but clearly A is not 0, or B is 0, and I don't want B to be 0. So I need to arrange them to be perpendicular. So how could we build a vector?
In the car, it's not there.
How could we build a vector that's perpendicular to this? So this is vector BA. That look about right for vector A. Trying to kind of sketch it on the XY plane. Just think of the graph and take the opposite M. So what do you want the new M to be? Somebody said, Sam Szymanski said, -3i plus 4j. Find a common multiple of 3 and 4. These are on the right track. What Sam said would be one pretty easy to pick off answer. One vector that works is, sorry, let me read that. Oh, you said -3i plus 4. Okay, I read it wrong. So Sam said to go -3 this way and +4 that way. -3 that way and +4 that way. I don't think that's actually going to work, Sam. Which quadrant do I want my vector to be in? Vector A is in the 4th quadrant. I want a vector that's either in quadrant 1 or quadrant 3. So we either want 2 positive coordinates for x and y, or we want 2 negative coordinates. We do want to flip the 4 and the 3, but we want them to have the same sign. So for example, flip the 4 and the 3 and give them both a positive sign. That would work. And so would any multiple of this vector. If you take this vector on the screen, which Titus wrote, and you multiply that by any number, any scalar, that would be another acceptable answer. Because if A times B is 0, so is A times a constant multiplying B. What would this one look like? Over 3 up 4, kind of like that. I know my picture is not great. This is one example of B, but in general, B has to be somewhere along this axis, making a 90-degree angle to A geometrically. So you could do 4i plus 3, or sorry, 3i plus 4j. You could do negative 3i minus 4j, or other things like that. So that's a couple thoughts. How can you just kind of verify that A and B will have a zero dot product? How do you do dot product with unit vectors? I times I, j times j added up. 4 times 3, positive 12. Negative 3 times 4, negative 12. It's a lot like what line is perpendicular to slope 3? The line perpendicular to slope 3 has a slope of negative 1/3. So if this line has a slope of negative 3/4, if the black line if the black vector is a slope of negative 3/4, I want to build a new vector perpendicular to that with a slope of positive 4/3, and this would do it pretty well. You could set up some algebra and do that, but probably geometry is the best way to go there. Thanks for your feedback there. Just think of the graph, take the opposite, find the common multiple. Good. What about number 2? The object A is going 1 meter per second. Imagine object A speeds up from 1 meter per second to 7 meters per second. It speeds up. At what speed along the way from 1 to 7 does it have kind of a midpoint kinetic energy between the kinetic energy of speed 1 and the kinetic energy of speed 7? I didn't say that very well, but what do you guys think about that one? Okay, so let me first of all say, what's the trap answer that's not right? What speed is halfway between 1 meter per second and 7 meters per second? Well, halfway between 1 and 7 is 5. Or sorry, halfway between 1 and 7 is 4, and 4 meters per second is not the answer we're looking for. Masses will cancel. That's true. I didn't give you a mass. I just said it's the same mass. So the mass part of kinetic energy is not very important to this problem. What's important to this problem is the stuff that's different. You know, Ka, Va, Kb, Vb, and then do another one for C. Does the mass matter in this problem? It's the same, so it doesn't really matter too much. You can put in whatever mass you want, and the answer would be the same. Does the 1/2 matter much in this problem? The 1/2 doesn't matter very much. You can throw it into your calculations. As long as you throw it into all your calculations, it'll cancel out. The core idea is, what is 1 squared and what is 7 squared? It's not velocity, it's velocity squared. What's 1 squared and what's 7 squared? Of course, 1 and 49. What number is halfway between 1 and 49? 25. So we want the new velocity to square to be 25, or we want the velocity of C to square to be 25. So the answer is, don't do 4 meters per second. You haven't hit half. You haven't. If you go from here 1 to 7 in 2 steps in energy, the middle step will get you to speed 5, and then the next dump of energy will only speed you up from 5 to 7. And that's because kinetic energy is quadratic in the velocity. You could set up a nice equation. You could do something like this. 1/2 m 1 meter per second squared plus 1/2 m 7 meters per second squared. If I add those and divide by 2, I want to get the kinetic energy of the third object. So you could solve that equation there and divide everything by m, and the m's are gone. Multiply everything by 2, and the 1/2s are gone. And then we're doing 1 squared plus 7 squared. Take the average, which is 25, and take the square root. So the answer is 5. Let me ask you this variation on number 2. What if we redid number 2, but instead of talking about kinetic energy, we talked about momentum? What speed gives you a momentum halfway between speed 1 meter per second and speed 7 meters per second? Momentum is linear in velocity, so that would just be halfway in between. So if you ask the question about momentum, 4 meters per second is halfway from 1 to 7 from the perspective of momentum because it's linear. But 5 meters per second is kind of halfway from 1 to 7 from the perspective of kinetic energy. All right, couple good warm-up questions. No real detailed calculations, but pick up your calculator, do a couple, plug in a couple numbers. Okay. If you give me a little bit of time here, I'm going to point to some of the practice materials, and I'm going to maybe do one of the questions or part of one of the questions together, and then I'm just going to kind of open it up after doing that one question together to questions from you guys. Which other questions would you like to look at, either from homework or from some of these resources on Moodle? So I'm going to share my screen here. Dun, dun, dun. And oh, that's not Moodle. That is Bible Gateway. Here we go. So March 23rd to the 29th, March 30th to April 5th. Test preparation materials and in here, practice energy and momentum problems was posted. Oh, picture, I'm glitching out. What are you guys seeing for me? Is it going crazy? Or now I'm frozen? Are you guys able to see me all right? Maybe? Okay. I don't know. My screen was having issues. It was making me wonder about my internet connection. You guys able to hear me, see me?
Yeah, I can hear you and see you.
Okay. All right, going back. Sorry. Maybe it was just my camera. Okay, so this one right here, practice energy momentum problems, that was posted a couple days ago. Now I've just moved it into this folder. It was questions without solutions. We did one or two of them together. Now there's solutions listed as well. And then if you click on more practice problems, I think there's one sheet with 4 questions and solutions are provided. So I'm not going to open those from there. I'm just going to, I already have them up on my screen. So let me make that bigger. Okay, so this was the practice questions. Oh, sorry. No, this is not the practice questions. We did these together the other day. This is the first one in the folder, or one of them in the folder, I should say. I'm just going to mention briefly on this one, any questions about circular motion are not relevant to the test. So number 2 and number 3 are not relevant to the test. We did number 1 briefly, I think a week ago. We did number 4 last Friday, I think. Those solutions are down below, but we already did them together. You could find them probably in your notes. Number 4 is relevant to the test. Number 6 is, this one's not relevant. Just ignore this one. The solution's not provided. It's not about energy or momentum. And then this question is relevant to the test. And here are the solutions. There's some answers. Solution to number 1, solution to that guy, and the ramp question. I really like the ramp question. I think you guys should take a peek at the ramp question right here. It's kind of interesting, especially part B. I think it's kind of a fun one to think about a little bit, and it would test your ability to recognize when is energy conserved and when is it not conserved, when is momentum conserved and when is it not conserved. That would definitely be one of the main skills for the test, is to be able to recognize in a problem when you can use conservation of momentum and when you can't, when you can use conservation of energy and when you cannot. You often can, but it's not always the case. So there's some solutions to that one. I think the problem I'd like to do is from the bottom of this one, which is just called more practice problems. Number 6 is really easy. Number 7 and number 8 are not too bad. I'd like to do number 9, but I'm just going to read 7 and 8. Number 7, a 12 kilogram ball moving east at 6 meters per second on a frictionless horizontal surface approaches a 5 kilogram ball moving west at 8 meters per second. In number 7, the two balls undergo a head-on collision and the heavier ball rebounds to the west, to the left, to the west at 2 meters per second. Find the direction and speed of the lightweight ball. What's the difference between 8 and 7? One word, well, maybe two words. Head-on collision was replaced with glancing collision. And west at 2 meters per second was replaced with north at 2 meters per second. So number 7 is a one-dimensional collision. Number 7 is one-dimensional, where like the two objects come together and bang off, due east-west, all motions are east or west. Number 8 starts out with purely east-west motion, but because they're not head-on, because they undergo a glancing collision, they start picking up some momentum, some velocity in the north and south directions as well. I'm gonna say, how would I do number 8? Momentum is a vector. How do you deal with vectors in 2 dimensions? You can use I-hats and J-hats, and that's equivalent to using, separating X components from Y components. So if I go down here, here is the solution for the head-on collision. I just conserved, this is really boring. For the head-on collision, I had a bunch of X information, meaning east-west, and what was my Y information for north-south? The first object wasn't going north or south. The second object wasn't going north or south. The final object doesn't end up going north or south, so the other final object doesn't end up going north or south. And it's just all zeros. How is this going to change if I go to 2 dimensions and the object exits to the north? V1 final X is 0 because the object's heading due north. V1 final Y is +2 and positive meaning the northward direction. So I am setting up the exact same 2 equations for the 2D problem as the 1D problem, but I'm just kind of putting some numbers that used to be 0 aren't 0 or vice versa. Okay, so here we go. This is conserving momentum in the X direction and then down here in the Y direction. The heavy guy starts out heading east at 6. The lightweight guy starts heading west at 8, which is -8. And then the lightweight guy, the heavy guy doesn't move east or west after the collision. That is 0 for the X direction. Which direction does the heavy guy move after the collision? 2 meters per second north. So I'm putting that in the Y, not in the X. And I have 2 equations. The first equation will allow me to calculate the X component of the lightweight velocity, lightweight object's velocity, and Y will get me the Y component. To conserve momentum right to left, the 5 kilogram object needs to rebound at 6.40 meters per second east or positive X. And it needs to rebound downward or negative Y at 4.80 meters per second. This is pretty easy math. Multiply, add, divide by 5. And let me go back to the question. The question asked for magnitude and direction. So right now I basically have X and Y components. I have I-hat and J-hat version, and I would just like to do a right triangle, 6.4 to the right, 4.8 south, east and south, and just draw the right triangle and find your angle and magnitude. The overall speed works out to be pretty much exactly 8 meters per second at an angle south of east. I-hat, J-hat, K-hat would be fine. I-hat, J-hat, K-hat is what did I call this? V2 final is 6.40 meters per second I-hat minus 4.80 meters per second J-hat. And overall, that is 8.00 meters per second at 36 whatever degrees south of east. Notice what I didn't do. I did not try to guess the direction at the start of the problem. I don't get the direction until the very, very, very end after having done my X work and my Y work independently of one another. Just because the three starting directions were really easy in the problem, we had due east, due west, and one thing went out due north. Just because those are all nice, easy to describe directions does not at all mean that the final object also ends up going at a nice, easy to describe direction. I need to dig into the numbers. I need to look at the speeds and the directions together and consider components. And you get this answer. What was I going to say? What was the initial speeds? Okay. I'm going to say one thing in passing. The numbers work out very nicely in terms of the math for the 2D collision I just showed you guys. It's probably not, it turns out everything's sped up in that problem, which is allowed by conservation of momentum, but it's not quite the way I wanted the numbers to work out. They work out as stated on the solutions. That's correct, but it's kind of weird because both objects end up speeding up in that problem. One object started at 6 meters per second, and one object started at 6 meters per second and ended up at 6 point. No, what was it? Oh no, sorry, that did work out better than I thought. Sorry, I'm all messed up. One object slowed down from 6 meters per second to 2 meters per second. How fast was the lightweight guy going before the collision? 8 meters per second. How fast is the lightweight guy going after the collision? Still 8 meters per second, but he just changed direction. It's coincidence, but that's the results. Okay, I'm going to talk about the problem at the bottom of that page, which involves a spring. But before doing that, I'm just going to kind of bring up a Word file, and I'm just going to type on the screen, here are the key objectives to be prepared for on the test on Monday. Sorry, I didn't get this written out ahead of time. I meant to. Key outcomes for unit number 3, which is conservation of momentum and energy. This is what I would say. As a student, ... am I able to, sorry, I meant to put the ... later. As a student, am I able to ... And now I'm just going to make a list. Am I able to, these would be the two really important ones, recognize when momentum conservation can be used. And number 2 is almost identical. Can I recognize when energy conservation, I'm going to say mechanical energy conservation, can be used? They are not the same question. They are two separate questions. Sometimes one is conserved and the other one is not conserved. Sometimes neither is conserved. Sometimes both are conserved. Those would be very important. If you don't have much of an instinct on that, that would be something to definitely think about and try to practice over the next couple days, because that'll give you kind of a good instinct on which kind of problems to approach via momentum and which kind of problems to approach via energy. I think a helpful example for number 1 and 2 is to think about the ballistic pendulum portion of the lab from a week ago. And that there's a Microsoft Stream video of that. You can look at that. That was a multi-step process where a ball slammed into the pendulum and then the pendulum swung upward. And during the first part of the process, momentum was conserved, the slamming together, and mechanical energy was not conserved. And during the upward swing, mechanical energy is conserved and momentum is not conserved. I will also point you to this question right here. This question right here, which is on the file called Practice Energy and Momentum Problems. The last question on this practice set, which is number 7, part B, both momentum and energy are conserved. You can see right here, number 7, is the horizontal momentum of the block ramp system conserved in part A? You're supposed to say yes or no. Is the mechanical energy of the block ramp system conserved in part A? Yes or no? Same questions in part B. And I'll just say the answers, you can see because I've provided the solutions. The answers here are yes for momentum on A, yes for momentum on B. No, sorry, I misspoke. I just totally misspoke. The answers are yes for mechanical energy on A and yes for mechanical energy on B. And the answers are no for momentum on A, yes for momentum on B. Okay, that's what I meant to say. What are some very specific things that you should be able to do? Can I set up and solve conservation of momentum conservation in 1D or 2D? Um, 1D, and then I'm just going to repeat that and say 2D. Okay, next up, I think those are the main ones on the momentum side of things. Can you recognize when it's conserved, and can you do it in 1D and 2D? There is one more for momentum. Am I able to recognize inelastic versus elastic collisions? And maybe I'm going to put a third category in here. Perfectly inelastic versus just plain old inelastic. Kind of a three-way comparison. Is it perfectly inelastic? Is it general inelastic? Or is it elastic? And you could maybe call this perfectly elastic. I'm thinking there of the Momentum Lab. The Momentum Lab with magnets. The red cart, blue cart would be pretty close to perfectly elastic. The Momentum Lab with Velcro is perfectly inelastic. Okay, so those are the momentum ones. And now I'm going to mention, I think, 3 for energy after mentioning 3, 4, 5 for momentum. Can I set up and solve momentum conservation? Can I set up and solve energy conservation with KE and PE gravity? Maybe one more, which relates to the problem I want to do, is can I set up and solve energy conservation with 3 or more energy contributions? And it could be this and this. It could be also PE of a spring. That could be another type of energy that could show up. What are some examples we've done where there's more than 2 types of energy? We've done a couple, like where the 2 objects were connected and one object went down and one object went up. How many contributions were there to the energy in those problems? 2 moving objects is 2 kinetic energies. 2 objects changing heights is 2 potential energies. So can I set up and solve energy conservation with 3 or more contributions? It could be KE, PE gravity, and PE spring. But another version of this would be, or like KE1 and KE2 and PEG1 and PEG2. Okay, So that's one example that we've seen a couple versions of. We especially did some problems like that on Wednesday. And they are, I think, worked out on Moodle partially or fully. I'm thinking they're very much of the question about the 15 kilogram block went down and the 20 kilogram block went down and the 15 kilogram block went up because they were connected by a rope. Last one for the key outcomes. Or can I calculate work using the dot product? And can I calculate work using the work energy theorem? I said one and I lied because I just wrote two. Okay. What's the work energy theorem? Work by non-conservative forces equals the change in KE plus the change in PE. That would be one good way to calculate the work. Another good way to calculate the work is use that dot product formula if that seems to fit the problem. Okay. Are there questions about some of these, like what I have in mind for some of these? I'll put this up on Moodle soon. I might change a couple wording. Okay, I'm going to look at the chat comments because I can't see it in the view I'm in. I'll put this up on Moodle soon, maybe changing the wording slightly. And somebody said, are you going to post this Moodle? Is there any on power? Okay, is there any on power? That's a good question. That's a very good question. We won't have any test questions about power. Power is a very easy step. It's one step away from energy, and it's a pretty easy step, but I'm not going to have any questions on the test about power. We've got enough stuff that I'm trying to cover already. We'll probably talk a little bit about power after the test on Wednesday, but there won't be any questions about power measured in watts on the test. Yeah. What's the definition of power, by the way? Energy per unit time. Number of joules divided by seconds divided by length of time. But that's not going to be on the test. All right. Okay. I am going to very briefly, I'm not going to go past 12:15. You guys should cut me off at 12:15. I'm going to very briefly show you an example of number 7 on this Word file. Can I set up and solve energy conservation with 3 or more energy contributions? The standard problems are like bullet point 6. Can I do conservation of energy with KE and PE? Just 2 energies. But the more interesting questions or the next step is, can I keep track of 3 or 4 or more energy contributions? KE, PE gravity, and PE spring. Here is an example of that. Which one should I click on? I should click on, not this one. More practice problems. More practice problems, and it's the 4th and final question right after the 2D collision. And I'm just going to talk through this one a little bit. A spring with spring constant 490 newtons per meter is standing on one end. It's on the floor and it's vertically positioned. A 5 kilogram block is placed just above it in the left picture and dropped or released. So the block is placed just above the top of the spring, and then somebody lets their hand go, lets it go, and it is dropped, beginning to compress the spring. What is the speed of the block after it has moved 5 centimeters downward? Is this a chance to use momentum? Is this a chance to use energy? I have height changes. If there's height changes, you probably don't want to use momentum. You probably want to use potential energy and energy. So we're going to use energy here. Is mechanical energy conserved, yes or no, as the block descends, as the block moves against the spring? Well, whoop. Oh, so many windows. Just a second. oh, this is what I called it, energy momentum equation sheet. Is do I get to use conservation of energy, mechanical energy? If there's no work by non-conservative forces, then I can use conservation of mechanical energy, which is potential plus kinetic plus potential. And which forces are acting in this problem? Gravity and the spring force. Both of those are conservative forces. There's no air resistance, there's no friction, so I get to use conservation mechanical energy. How many terms will be on the left-hand side of the equation? How many terms will be on the right? I have an object changing speed. I should put kinetic energy on both sides. I have an object changing height or y coordinate. I should put potential energy on both sides. I have a spring that is changing length. And if we look up here, spring potential energy depends on x, which means the length of the spring. You could also call that s, the length of the spring. So I need to have 3 energies in the initial state and 3 energies in the final state. Okay, I have 1 minute to say anything else I'm going to say about this. And what I'm going to say is the initial state is really, really easy. I just got to get down there. How fast is this block moving at the start? It's released from rest, no KE. I'm going to call this, how much has the spring been stretched or compressed from equilibrium at the start? The spring is at its relaxed position at the start, so there's no spring potential energy at the start. And if I measure all the heights from here, notice I called this height y equals 0, then the block starts at height 0, which means I can just say it starts at gravitational potential energy 0. So I'm going to do that, and I'm going to say the initial energy is 0 plus 0 plus 0 is 0. KE1 plus PEG1 plus PES1 is the same thing with 2's, and everything starts at 0. And then where does the 5 centimeters go? It is, what is the final height? Well, if the starting height is 0 and you went down 5 centimeters, the final height right here is negative 5 centimeters for final y coordinate, and the compression of the spring is equivalent. The compression of the spring is negative 5 centimeters. However, in the spring PE formula, you square kx, so it doesn't really matter that this number is negative because it's going to get squared in doing 1/2 kx squared, but it really, really matters that the object went vertically downward, and we'd better put a negative height change, final height in to the PE. And you can work it out and you get this speed right here.
It's 1216.
What was that?
It's 1216.
Yeah, it's like
to cut you off.
Yeah. Yeah. Oh, I thought you were saying something else. Thank you for doing that. I was cutting myself off, but thank you for cutting me off. There is some snow outside the window. Holy cow. Yeah. Yes, thanks. Okay, so at this point, I'm just going to ask you guys if you have some homework questions you would like to talk about. And we could do that. And if that takes the rest of the 15 minutes or less, 12 minutes, whatever it is, that's great. And if not, I think I might go back to that spring problem and kind of point out a couple other things to that. But keep in mind, conservation of energy is not always 2 things on the left, 2 things on the right. You have to think through how many different energies are relevant. Somebody said chapter 1161, the final part. Any other nominations from, I think everything's from chapter 11. 41, a part of 41, 61, a part of 61. Oops, I'm in the wrong chapter. Let me just glance at these. Oh yeah, 41. Forgot about 41. Parts A through I. What is that? 9 parts, I think. A, B, C, D, E, F, G. 9 parts. And 61 has 5 parts. Yeah. Yes. Okay. Let's see. I'm glancing at those. Do people have one or the other they'd rather look at, or are there other questions that people still have on their minds? Okay. Number 61 is about a force involving sine, the sine function. And okay. Part E is definitely, I think, the trickiest part of number 61, Darren. I think I'm going to do the 41 question first, unless there's a big outcry, because number 61E is important for the homework, but it involves doing the integral of force dx. And I'm not going to have any integrals force. I'm not going to have you calculate work on the test on Monday with a variable force. And sine, of course, varies from high to low. So I think with the test on Monday in mind, I think I'm going to kind of look at 41 first. We're given a graph on 41 of velocity, and A and B are review questions from like our first unit. Part C, kinetic energy versus time. What's the kinetic energy graph going to look like? The velocity graph is linear up, linear down, flat. Kinetic energy, you have to square velocity. So when the velocity is linear, I think if you apply the kinetic energy formula, you'll get something kind of parabolic upward, and then kind of parabolically coming down, and then it'll be level. When the velocity is level, the kinetic energy will be level. So I'm just kind of quickly thinking through A, B, C, D, E, F. Force versus time, that's very similar to the acceleration versus time graph. If you can draw the graph for part A, all you have to do is multiply by mass, and you'll get a very similar looking graph for part D. Did they give us a mass, 500 gram mass or half a kilogram? Okay. Part G, okay. Force versus position. This requires no calculations. Just think carefully about what you learned in the first 4 parts of the graph. All right. Oh yeah, that is a little tricky. They're saying it requires no new calculations. So let me see here. So very quickly, what does the force graph look like? Force is proportional to acceleration. Acceleration is the slope of velocity. So the slope, what's the starting slope? Can somebody tell me that? 20 over 2 is 10. So the acceleration and the force look a little bit like this. A little bit too high. What's the force for the first 2 seconds? Slope is 10 meters per second squared, and the mass is half a kilogram. So 5 newtons. Is that what anybody else got for the first 2 seconds? If this is force. I'm thinking of part D. And then what's the force from 2 to 3 seconds? Oh, what's the slope from 2 to 3 seconds? -5? Okay, I thought so, but I wasn't sure. Let me come down here to -5. Maybe something like this. Doesn't really matter to me too much. And we get to 3 seconds. And then this force is 0 to 4 seconds. Does that sound about right? Something like that. So if you're graphing force versus position, I think all you have to do is you have to figure out what is the position of the object at 2 seconds, what is the position of the object at 3 seconds, and what is the position of the object at 4 seconds. If you know those values, I think you can adjust this. You'll just kind of replace t with x, and instead of 2 seconds, you get a position. So where is the object after 2 seconds? How do you use the graph provided to do that? That would basically be part B. It starts at 0, and you use the area under the graph provided to find where the object is 2 seconds after the start, where the object is 3 seconds after the start, where the object is 4 seconds after the start. Okay? Can anyone tell us that? Can anyone tell us what's okay, I'll say this. What's the position at 0 seconds? I think that is 0 meters, right? What's the position at 2 seconds? Can somebody just tell us that? 20 meters, says somebody. I believe you. I think that sounds good. How'd you get 20 meters, Elizabeth? Area under the curve is triangular. What about position at 3 seconds? I think it's a smaller position than at 2 seconds. I think, oh, I'm trying to do it in my head. 1 times, is it 5? Is it 5 meters after 3 seconds? I think it's 5 meters. Right? Yes, no, anybody? And position at 4 seconds. Kind of a good review of previous work. 10 times 1. I think it might be 15 meters, I think. If somebody wants to agree or disagree, go ahead. So I would just take this graph and I would draw a new one where you stay at 5 newtons from 0 to 20 meters. You stay at negative 5 newtons from 20 meters down to 5. Oh yeah, that is a little strange, isn't it? I think I said something strange. Anyways, I think those are the key numbers. You just need to kind of connect those dots. Let me think about that. Fx versus x to determine, oh, sorry, force versus position. Yeah. So it's strange. Yeah. What do they have this in the back of the book? I'm sorry, I'm not too up to speed on this question. Huh. Oh, sorry, I messed up. I didn't mean to say, forget what I said about 3 seconds and 4 seconds. For some reason, I subtracted. I was supposed to add. Forget what I said about 3 seconds. That was terrible. Oh boy. And it made the problem nonsensical. Position at 3 seconds is 35. Yeah, I did, for some reason, I did 20 minus 15 is 5, and I was supposed to do 20 plus 15. That was dumb. And the actual position at 4 seconds is 35 plus 10 is 45. Okay, is that right? I think that's right. So from 0 to 20 at height 5, from 20 to 35 at height negative 5 newtons, from 35 to 45 at height 0. Just some kind of graph exercises. Okay. Let's see. I think I'm going to talk about 61, which somebody asked about. That one also involves some calculus. Number 41 involved calculus, but you could do it graphically by using areas under the curves and slopes. Number 61 gave you a formula which involves sine, sinusoidal sine function. And so you have to do some calculus. You have to do an integral of the sine function to find the work. And that is relevant to part E. So you have to do an integral of f dx for part E. And I think I'll kind of try to talk through that a little bit here. Trying to find the numbers here. Okay. What does a sine wave look like? Let's try this. This isn't going to, well, you know, what does a sine wave look like? You guys see that? It's not great. Should have used a different color. Okay. So at what let's talk about part C. What is this position? I'm going to say force reaches a maximum right there, right? What is this position? It is 1/4 of the period. What's the period of this? Or you could say the wavelength almost. What's the wavelength of this? 2 pi over c. Does that sound familiar? 2 pi over c. And what will x max be? I think, is it correct to say that it's 1/4 of that? Does that sound correct if people have done number 61? X max should be 1/4 of the period. Yes, no, maybe? Anybody? And most of the question is about that. Okay. A particle of mass m starts with a positive velocity. Okay. How do we apply energy concepts to this equation right here? I'm going to use the work energy theorem, and I'm going to use the definition of work in terms of force and distance. So the equation I want to use is this. The work is the change in kinetic energy. That is equal to 1/2 m final velocity squared minus initial velocity squared. Does that seem reasonable? And what's the work? The work is the integral of force dx. So they said V naught should be in the answer. There's V naught. They said M should be in the answer. I've got some M's. And then they said all the stuff applying to force should be in the answer, like F naught and C. And what should I integrate from? I should integrate from the starting position. This is like X naught, and this is like the final X. So integrate from x0 equals 0, and keep integrating until you get to x final, which in this case is pi over 2c. Okay. This is what I would do. If you want to stick around and see a little bit more about that, we can. What's the antiderivative of sine? Negative cosine. So, sorry, I meant to draw this in here. This has to do with the area under the curve. The area under the curve is the work, and the work is not the final KE, the work is the change in KE. And I want to find that area. And if, negative cosine, yeah. So the antiderivative, I think if you do it out very fully, and if you guys want to leave or sign off, you're dismissed, just saying, if you want to do this very fully, I would say F0 sine of Cx dx. And for right now, I'm just going to say delta K. Or maybe I'll just say delta K over here. And I'm going to integrate from 0 to whatever position you labeled in number part C. And I think it is pi over 2c. And then the antiderivative with respect to x. And can somebody type in what's the antiderivative of this with respect to x? And I think I would get a negative cosine. So I'd get negative f times cosine of cx. But what else do I have to do? I have to divide by the coefficient of x inside of the sine function. So I need to divide by c. So I think overall, I would say I would get this. You see that answer there? Negative f over c times cosine cx. And if you want to double check, just try taking the derivative of that formula and see if you get back to f sine cx. I think you probably do. And I think at this point, maybe we're doing all right. So now I've got negative f over c times cosine of cx. And I need to evaluate it from the starting endpoint of 0 to the final endpoint. I lost my markers. Oh, behind the book. What's the starting endpoint? 0. What's the ending endpoint? Pi over 2 times c. And maybe I should do this. And I think it's not too bad from here on if you were to kind of give this a shot. What do I get when I plug in pi over 2c? Pi over 2c times c, pi over 2. What's the cosine of pi over 2? 0. So the upper endpoint gives 0. And then I should plug in the lower endpoint. I don't know if you guys can see that. You should plug in the lower endpoint. And what do you get when you plug in 0 to cosine? Cosine of 0 is 1. So I get negative f over c times 1. And what is the overall result for the integral? And the integral represents work. And you could also say the integral represents change in kinetic energy. So what's the overall result? Positive f over c. Or I think they called it f naught, and I haven't been writing f naught. Okay, and if you set this equal to the change in, kinetic energy, you can solve for V naught and get the formula that they have in mind for part E. Yes, no, maybe? Any thoughts? All right, this F over C is the area of this shaded chunk. At what position X max does the force first reach a maximum value? Yeah, I'm just double checking that I read this how I meant to. All right. Yeah. Thumbs up, thumbs down. You think it works? Okay. If you have questions, just stick around and ask, please. That'd be fine. This would be a good time to do that. I think I've said what I'm going to say here. The rest of the problem is to do F over C is the change in kinetic energy, and to solve this for VF. Okay. Have a good weekend. Look for posting on Moodle probably for like 5 o'clock, maybe on Sunday, maybe 6 o'clock, 6 o'clock on Sunday. I think I'll be available on Moodle to ask questions, kind of like an office hour the night before the test. Thumbs up, thumbs up. Thank you guys. Thanks everybody. Hey Ashley, hey Rockford.